Hello guys, today we're gonna be talking about the Unet architecture. We're gonna be diving deep into it, understanding it, and at the end we're gonna be implementing it from scratch. So to me, Unet is really a great way to get into deep learning, to learn how to design really powerful deep learning architectures to achieve various tasks. Really, so usually what I usually recommend is that when you want to learn any deep learning topic is to go on, read the original paper and possibly implement it yourself. So the original paper for UNET is this one over here, UNET Convolutional Networks for Biomedical Image Segmentation. Um, it was released in 2015, so it's a really an old paper. And it really came out after deep convolutional networks were really taken over, and it was used to segment medical images. And by segmentation, I mean putting labels. So let's say you have an image of cancer. So you'd be coloring the cancerous part by, let's say, by red, and the rest of the image by black. We're gonna be implementing the paper later on, so you're gonna see an example yourself and really understand what segmentation is. So don't really worry about it for the moment. Um, so as I just said, UNet was used for segmentation. So let's take an example on what segmentation is. So segmentation is basically finding a certain part in an image. Let's say you have an image and you wanna find the pedestrians, or you have an image containing a dog and you wanna find the dog. So in the original paper, they give an example where you have an image of a cell, and you really wanna find the cell. So the output image would be an image where the cell would be colored with a different color. Over here it's colored with blue, and the rest would be colored with black. So the network would output an image with basically like two colors, blue for the cell, and what is not the cell would be colored with black. Now actually here it outputs three colors: the border with yellow, the inside of the cell with blue, and the rest was black, but it's the same thing. So this is what the UNet tries to achieve, and it actually achieves it in a really great way. It actually revolutionized convolutional networks. So let's take a look at the architecture. This bad boy over here. Now it's called the UNet mainly because it's shaped like the color U. So it's like the color U, as you can see over here. So before diving into the architecture, let's first take a look at some of the mathematical operations that it achieves. So the first one is convolution, and convolution in plain English language it means filtering. Okay, so the first operation it achieves is filtering, and the way I put an example over here to help you really understand it. So let's say we have this image. It's a 3 by 3 image, so it's a really tiny image, and we have this 2 by 2 filter. What we do in convolution is that we start making the filter pass above the image. So first the filter would be above here, so it would take 1, 2, 4, and 5, and then it would do element by element multiplication. So the 1 would be multiplied by the 1, the 2 with the 0, the 4 with the 0, and the 5 with the minus 1. Then we add, as you can see over here, we get minus 4. And this would make the first element of our new network, so of our new image. So minus 4. Then we make the filter pass again. So initially it was here. Now we move it to the right. Now the filter would be here. And then we do it again. 2 multiplied by 1, 2. Then 3 multiplied by 0, 0. Then 5 multiplied by 0, 0. Then 6 multiplied by minus 1. We get this over here, and we get minus 4. Then we do it again. So we make the filter move. It becomes over here. and then we do element by element multiplication, as you can see over here. So here we have the same filter every time. That's why I didn't rewrite it. So we have 1, 2, 4, 5, and we do element by element multiplication. Now, like it was a chance that they all turned out to be -4, but it's just a coincidence. So this is filtering. Basically, you pass a filter above the image, and when you do it, you generate a new image, a filtered image, really. And it is the first operation that's done in the paper. And the goal behind doing a filter is basically, let's say you are searching for the edges. Okay, so let's say you are searching for the edges in an image. So there are certain types of filters that can help you detect edges. Okay, let's say you are searching for the color red. So you can design this matrix in a way that you just find the pixels that are colored by red, and so on. So convolution is basically filtering. This is the first type of operation. Now the ReLU. The ReLU is actually a mathematical function. It takes an input, a number, and it outputs a maximum between 0 and this number. So basically, it's like, okay, if you're negative, I'm gonna take 0 instead, and if you're not negative, I'm gonna take Q. So if we wanna design, if we wanna draw the curve of this function, basically, so I'm gonna draw it with red. For all negative numbers, it's 0, and then it becomes y equal x. So for 1, you will have 1. For 2, you will have 2. And for everything else, it would be 0. So it's a maximum between 0 and x. So we're gonna apply it to our output over here. This is a filtered output. So we made the filter k pass over the image. We got this output -4 everywhere. And basically, because it takes a maximum between 0 and x, it's gonna take 0 everywhere. Alright? So this is the second operation that's used by the paper. And now for the final operation, really, to understand the Unet paper, we're gonna understand the up convolution, also called deconvolution. And when I say deconvolution, it basically means defiltering. Okay, so it's a better name would be deconvolution. And when I say deconvolution, it means defiltering. So it's the inverse of what we did earlier. So first, to help understand it, let's say we have this filter. Okay, a filter is also called a convolutional kernel. Okay, so just like a naming convention. So we have this filter k, and we do exactly what we did earlier. Okay, so here is our input image of size 2 by 2. That's a very small image. We take the 1, alright, and basically we multiply it by k. So I demonstrated it over here. So step 1, we take x11, which is like, we take x11, which is basically the first element of x over here. So this is x11. We take the 1, and we multiply it by k. So we get 1 multiplied by k, which is k. So we get 1, 2, 3, 4. This is step 1. Then, and we place it at the top of our new matrix. So our new matrix would be equal in size to x multiplied by 2. So x is 2 by 2. Our new matrix would be 4 by 4. Okay? So let me delete a bit. So now we take x12 in our second step, which is 2. And we also multiply it by k. We would get 2k, which is 2, 4, 6, 8. So 2, 4, 6, 8, and we multiply and we place it at the top of our new matrix. Then we take x 21, which is 3. We multiply it by k, we get 3k. We place it down here, so we get 3, 6, 9, 12. Then we take x22, which is 4. We multiply it by k, we get 4k, and we place it over here, and voila, we at the end we just like add these four and we get this. So this is 1k, this is 2k, 3k, and 4k. And 1k is basically x11 multiplied by k, 2k by so this is x11 multiplied by k, this is x12 multiplied by k, x21 and x22. So this is a deconvolution. So basically a convolution, it keeps the size of the image. So the convolution, the first operation we explained, it keeps the size of the image, just it like filters it. A ReLU, it takes the maximum between 0 and x. And a deconvolution, it's the inverse. So instead of, so it at first it increases the size of the image, and it also like applies a certain type of, it's not filtering, it's defiltering. I hope it's clear. And now for our final operation, we have the max pooling. And what the max pooling is basically it every time it takes a pool of 4 pixels, so let's say these 4 pixels, and it chooses the maximum. So that's max pooling. So in our first example we have 4, okay? Then we do the same for the next 4 pixels. So out of these 4 pixels we also take the maximum, which would be 8. So we have 8. And then we do it again. So for these 4 pixels we take the maximum, which would be 12. So here we write 12, and then we do the same. So out of these 4 pixels we take also the maximum, which would be 16. So here we have 16. And as you can see, we started with an image of size 4x4 over here, and we ended up with an image of size 2x2. And this is really vital. So the max pooling shrinks the image by half. And so as a final overview, like Unet uses these operations to do the following. We first start with a really big image. Okay, so we start with this really big image. We generate really tiny images. Let's say one image would be would find the ear of the cat. One image may find the eye of the cat. Okay, one image may find like the white part, like this part. So basically, at the first part, at the encoder part, the Unet shrinks the very big image to really, really tiny images, many tiny images. Let's say 1024. So we start with an image of size 570 by 570. At the end of the first step, we end up with 1024 tiny images, let's say of size 30 by 30. Okay? And these images would capture low level details like where the eye is, where the ear is, I don't know. Like these details are learned by the network. And at the next stage, okay, we take these really tiny images. Let me put 3 dots so you can know that we have 1024 images. And at every step, we start grouping, kind of like grouping them together in search for where the cat is. And as I said earlier, our final goal is to find like this semantic label. So to generate an image like this where we have the cat colored with green and the rest like colored with a different color. So let's see how Unet does the overviews that I just described now. So now we have an idea of each different type of operation that this network does. Now we're gonna go into fine details about the architecture itself. So as I said earlier, it's called the Unet because it follows the shape U, and it's made of 2 parts. The first part, I'm gonna draw it with red, is this part over here. It's called the encoder. And the encoder basically compresses the image, and we go from really big image to really tiny images. So we have initially one image. At the very end, we'd have 1024 tiny images of size 30 by 30. They're really tiny images, and each one captures a certain detail. So let's say we have our image over here, and we're trying to detect where the cat is. So the cat is, our network should output something like this. It's like around where the cat is. The encoder would take a very big image of, let's say, size 572 by 572, and it would output many tiny images of size 30 by 30, and it output like 1024 images, and each one would capture a certain detail. Like, for example, one may capture where the ear is, so it would just output the ear of the cat. One may capture where the eye is, so one filter, one output of the encoder may be an eye, the eye of the cat, so it would be over here. One may detect the white parts of the cat. I don't know. Like, it depends what the model learns to filter on. So the encoder basically captures really fine details in the image to help the network detect where the cat is. So this is the first part. The second part, I'm gonna draw it in blue, is the decoder. And the decoder does the exact opposite of the encoder. So it takes many small images, and it outputs a really big image containing where the cat is. So the encoder takes a really big image, and it outputs really tiny images, 1024 images that capture details. However, the decoder takes many small images, 1024 small images, and it outputs a big image of where the cat actually is. So now let's go into details of level by level how it does what it does. So first, we're going to be talking about the encoder and how it does what it does. So initially, let's take the first level. So we're talking about here. We have a really big image of size 572 by 572. We go by the blue arrow, and if you go over here, the blue arrow is a convolution followed by a ReLU. So as I explained earlier in the operations, a convolution is basically a filter. So we pass the image by 64 filters of size 3 by 3. So we have our input image, we pass it by 64 filters, and the 64 filters would be filtering on something that will help the network later on detect the cat. So maybe one filter would be find the edges, one filter maybe find the red parts of the image. So we pass it by 64 different filters, and as a result, each filter generates a new image. We'd have 64 images, all of size 570 by 570. Just a side note that we lose 2 pixels on the boundary because we can't really pass the filter on the boundary. So let's say we have our image over here. We start passing the filter and generating the image. At the boundary level, we can't really put the filter, and that's why we lose 2 pixels. Then we do it again. However, so the first time we have 3 by 3 filters, and we have 64 in total. The next time, just like, you have to pay attention that after the first filtering, we no longer have an image of size 572 by 572. You have an image that has a depth, and the depth is 64. So let's say this was our image initially. When we passed it by the 64 filters, the image now has a depth. So it's made up of many images of the same size. And as a result, the next time we want to apply a filter, the filter can't be 3 by 3. It has to have a depth as well. So the filter, the next time we pass it by, would be 3 by 3 by 64. Because it needs to pass by all the images that make up the image. As a result, the images will become of size 568 by 568, but we want the output to stay at 64, so we pass it also by 64 different filters. So let me go again. Initially we have one image, we pass it by 64 filters of size 3 by 3, and we generate an image with a new depth of 64. So it has a depth in the z direction. Then we do the filtering process again. However, the image is no longer of size 572 by 572 by 1. It has a depth now. So the filter that we will put should account for this depth, and that's why it would be 3 by 3 by 64. And because we want to apply many filters, we apply 64 filters of this size. Then we do max pooling, and max pooling is, as I explained earlier, is basically out of every 4 pixels we take the maximum one. So it was explained over here. So let's say here we have 1, 2, 3, and 4. We would take the 4, 2, 4, 6, and 8. We would take the 8. Here 4, 8, 6, and 16. We take the 16, and this would be the generated image. As you can see, the image shrank by half. So we had 4 by 4, it became 2 by 2, and this will also happen here. So as you can see, max pooling is the red arrow. So when we do max pooling, the image would go from 568 by 568 to 284 by 284, and it would keep the same depths. Then we do convolution again. However, the filter would be of size 3 by 3 by 64. Accounting to the same depths of the image. However, we want to increase the depths to 128, so we apply 128 different filters. Okay? And then we do a relo, then we do it again. However, the next time we do, so we're over here now, the next time we do it, it has to be 3 by 3, not by 64, because the depth is now 128, by 128, so every filter would have this dimension. And we will also be applying 128 different filters of this size. Then we do max pooling again, so the image decreases by half. Now we're at 140 by 140. Then we apply 256 different filters of size, instead of 128. The first time it would be 128, but the next time the depth is 256, so we put 256 over here, and so on. We keep doing it. So we pass like this, this, and at this time, like when we reach here, we're at the bottleneck, and at the bottleneck, the network would have really tiny images of size 28 by 28 and of depth 1024. Okay, so this is regarding the encoder and how it achieves its task. So before we get into how the decoder achieves the final task of detecting where the cat is using these really small images, we have to first talk about a really vital operation that the Unet does, and it's called the skip connections. So basically, let's say you have this neural network, and let's say it has a really big depth. So here we have just 4, let's say it has even way more. So we have also a layer over here, and so on. Okay. As you can see, the first layer 1 over here, it sees the input. Okay, so it sees the input images. The last layer over here, by the way, this is a stack of layers. So let's say here we have 5 hidden layers. Here we have 3. Here we have 2. Here we have 5. Here we have 5, here we have 2, and let's say here we have the final layer. So I'm just gonna draw a small rectangle. The last layer, between the last layer and the input layer, we have 5, 3, 2, 10, 20, we have 22 layers. So as you can see, and each one of these layers is like applying a different activation function. So by the time the input passes by all the layers and reaches the final layer, it has already been deformed too much. So the last layer really will not see the input layer, will not see the input. Okay, so the last layer will not see the input. And also, so we calculate the output at the last layer, then we calculate the loss, and we want to apply gradient descent. And as you know, there's a chain rule being applied. So the loss of this layer would be calculated by applying the loss. So here we have the loss function. We calculate the derivative with respect to the weights of the last layer, and we apply chain rule to update this layer. Then we apply chain rule again. By the time we reach here, the gradient of the first layer with respect to the loss, the gradient of the loss with respect to the weights of the first layer, because we're applying chain rule so many times, and because the weights are usually initialized to 0, so they're like noised, so the weights are noised, really the gradient will not be calculated correctly because it's noised too much. So if we try to draw the curve of the loss with respect to the number of epochs, we'll see that it really struggles to start converging. Let's say here we're at epoch 1000, it starts to go down. And the reason is because, first of all, as I said, the last layer doesn't really see the input. And also, when we apply gradient descent, the chain rule will not work correctly because we initialize the weights to 0. And by the time we're trying to update the first layer, it has already been corrupted by noise so many times. So let me now delete. And the solution to this problem, to make the network converge way faster, is to do a skip connection. So the skip connection, it solves the two problems I spoke of. First of all, the last layer starts seeing the input, and also like the output of layers behind it. And the second solution is when we apply gradient descent, so we calculate the loss, it can propagate over here. So we'll update the weights of the first layer really early on. So that's what they did in the Unet. So they start doing skip connections. And the way you do skip connections is like, there's two ways. The first way is you just simply add. So let's say you have the output of this layer. You add it to this layer. However, that's not how they did it in Unet. Instead of adding them, they concatenated. So let's say this is the first image, this is the second image. Instead of adding them, you concatenate them. So you will end up with a new image of which is like the two images like placed next to each other, and that's concatenation. I hope it's clear. So now we are ready to see how the decoder achieves its task. And basically, it does the exact opposite as I said, and it uses these skip connections. Like you can see it over here, over here, over here, and over here. So, as a reminder, at the end of the encoder, at the bottleneck, we have images of size 28 by 28 and of depth 1024. And I described it like being 28 by 28 image, really tiny images, many tiny images, but it's actually like one image of really big depths. And then we do an up convolution, and I explained the up convolution really early on. I said it's like the opposite of the filtering process because it so you can revisit that part of the video, but it first of all it doubles the dimension. So as a reminder, we had an input image of size 2 by 2. Here, the output was of size 4 by 4. So when we apply the up convolution, we have 28 by 28. It will become. Why does this look like a 4? This is a 8, not a 4. So we should have 56 by 56. Also, so we pass many filters and we do the up convolution process I explained earlier. However, as a reminder, the filter should match the depths, and the depths in this case is 1024. So every filter should be of size 2 by 2 and depths 1024. So this is the size of every filter. So let me color it in red. This is the size of the filter, S filter, okay, and the amount of filters we should have, we have 512, we have 1024, but we want to decrease the depths by 2, so we should have 512 different filters. So, in conclusion, we would have 512 different filters of size 2 by 2 and depth 1024. And what happens is that we apply the deconvolution process I explained earlier in the video, and we double the length and width, so we would have 56 by 56 and depth 512. Then we use the skip connection and we go to the parallel. So here we have decoder level 3, level 3 or 4, level 3. We would take the output of the encoder level 3, which should have details, like really zoomed in details, and we would concatenate them. Concatenating them basically increases the depth, so we concatenate them alongside the depths. So every one of them has depth 512. So this one has 512. So we would have a depth of 1024, and here we have the 512 images of the encoder, the 512 of the decoder. We concatenate them. Then we pass them by another filter. As I said, it should have the same depth, so it would have a depth of 1024, and it would be of size 3 by 3, and the new depths of the image should be 512, so we should apply 512 different filters. Then we do it again. So we apply again 512 different filters of not the size, because depths just changed. So over here the depths changed, so this should be 512. Then we do up convolution again. So we double the size of the image. So instead of 52 by 52, we should have 104 by 104. And we want a depth of 256, so we apply 256 different filters. We concatenate with the parallel to it from the encoder layer, which should be this one over here. So we do a skip connection. We concatenate. So this one has a depth of 256. This has a depth of 256. When we concatenate them, we would have a depth of 512. Then this new image of 512, which has from the encoder the fine level details and from the decoder like the zoomed out information, this new image would be filtered out to help us more and more find where the cat is. And we redo it again and again until so this is the decoder. We would pass like this until we reach here. Then we apply many filters, and finally at the very end, instead of applying a filter of size 3 by 3, we apply a filter of size 1 by 1. And it depends what you want to output. If you want to output one image, you would apply one filter at the end. If you want to apply if you want two images, you apply two outputs at the end, and that's it. So this was really an overview of how the Unet works. So I will go over it again really quickly. At the encoder level, we apply convolutions and we downsample to get an image at the end of very small lengths and widths, but very big depths. And this image would every layer of this depth would capture fine details. And then at the decoder, we do the exact opposite. So we also apply a filter, and the filter should match the depths. So let's say here we have 1024. So the filter should have a depth of 1024. This is very important for your implementation, guys. And it would have a length of 2 by 2, and we would be like sliding it alongside the image. And the amount of filters we apply depends on how many images we want, on how much the new depths should be. And in the decoder, our goal is to decrease the depths. And because we want to decrease the depths, we have 1024 here. We should have 512, so we should apply 512 different filters. we concatenate from the output of the encoder layer. We concatenate them, then we apply filter to this new image. That's a concatenation between the decoder and the encoder. We apply up convolution again. We should have 256, so we apply 256 different filters. We concatenate with the skip connection, and we keep doing it until we arrive to the output layer over here. And one more thing I have to mention, guys, is that the weights of every filter are, so we have a filter, let's say, I really have to stress this. So let's say we have this filter over here. It should have weights W1, W2, W3, and W4. These filters are learned by the network, so we humans don't control them. So when I was saying in the video, one filter may be detecting the black color, one may be detecting the eyes. Actually, I don't know. I'm just giving an example. These weights are learned by the network via gradient descent. Now we're gonna be taking a look at an implementation that I did on Collab. So where is it? Unet. So this is my implement. I'll be linking it in the description for you guys, and I'll be linking two stuff. Like one is the final implementation, and one would be like an implementation that's missing a few lines for you guys to practice, because if you just watch the video you won't really learn. So I'll be removing some of the lines, and like I'll make it like a lab for you guys to exercise. So first, before we start, you have to change runtime type and run it with the GPU. So we start running it, and here in using device, it should be printing that it's using CUDA. So this is the very first step, really. So hello guys, so in our first part we already did the imports and we made sure that we're using CUDA, we're using our GPU for faster training. Now for the second part we're going to be loading the data, and I chose the Oxford 3 PET dataset. You can go and read its documentation, but basically you have to specify if you're doing, if you want a train val or a test in your split argument, and you have to specify what type of training you're doing. Our training task here is segmentation, so we're trying to label, let's say, where a cat is. So we specify target type equals segmentation, and we also have to specify a list of transformations to be done on the image, and that's so here I loaded the data for the dataset and for the testing, and here are the lists of transforms. So first of all, for the image, I use torchvision.transforms, and the resize transform basically resize an image to what you want it to be. So I don't know in what size it comes. However, I wanted really small images, so I specified 128 by 128. Then these images come in the PIL format, and if you don't know, PIL is like every color is represented by a number between 0 and 255, but I wanted it to be a number between 0 and 1, and so I did the torchvision.transforms to tensor. So first I resize, then I did to tensor, and to apply my transformations in this order, I do the dot compose, and this dot compose basically takes a list of transformations to be done. And this is regarding the image. However, there's also a mask, and there's a mask because we're doing segmentation. And if you don't know, a mask is something like this. So here's your original image, and here's your segmentation mask. So basically it's also an image. However, instead of colors, we have labels, so 0 or 1. So here, let's say we have 1, 1, 1 for every pixel, and for the colored part we have 0, 0, 0, and it's basically where it specifies where the person is. So this is basically our labels for our training. So we have training and we have labels, and we're trying to teach the model how to predict the correct labels. in its segmentation. So for the mask, I first of all I resized, okay, and the interpolation part is not really necessary, but I figured you may like be using a different data set. So here we do an interpolation dot nearest, so we don't want a number that's decimal. We want, let's say it contained 1.8 for some reason. We take the 2, okay. Then unlike the uh, unlike above, here we want it to be a number between we want it to be a value like 1, 2, or 3. So I did a PIL to tensor. Then like if you read the documentation, you'll see that the labels come in values 1, 2, 3. However, I wanted them here to be 0, 1, or 2, and that's why I added this lambda function, which takes a number, subtracts 1. Okay, and just to be sure, I clamped it between 0 and 2, just to be sure. However, it's not really necessary, like, because if you just apply this function, every number that's in the input will be subtracted by 1, and that's it for loading the data. Then we run our cell over here. It should download the data, and yeah, that's it. We have our data set. Okay, let it run. Now, after it, I just added a visualization so we can like visualize the data. So I'm gonna also let it run. We'll come back to it in a second. So I paused the video so you don't have to wait with me. So that's it. We downloaded the data set, and so I printed the lengths of the data set and of the test data set and of the train and of the val. You can see it over here. And then we visualize. So here's the image. Here's is the ground truth mask, and we're trying to predict something similar to the ground truth mask. So as you can see, like we have red, black, and we have white. You're gonna ask me why are the colors like this? We specify them over here in our plot. So I used black, red, and white. You can choose whatever colors you want. And now for the bad boy over here, the architecture. So first, before we read the up convolution and the convolution block, let's first look at the forward. So what's the forward? The forward is basically the architecture over here. So as you can see, like you design your architecture, now you first write the code of the forward. First we take the image, okay? So here's our input image. We first have to do the first encoder, all right? So we have to apply the first encoding, okay? So we do s1 equals self dot inc1 of x, and as you can see, x is initially of batch size h and w, and when we do our first encode, it's gonna become of size batch size. It's gonna stay batch size. However, we're gonna have a depth of 32, because we're specifying here that we want 32 different filters to be applied. Then we do a self dot pool one, and it's a max pooling. And as I said, the max pooling divides height and width by 2. So first of all, we did this. This is the self dot inc1. So this is the inc1. Then this arrow over here that does max pooling is pool 1, okay? And after it, we do s2 equals self dot inc2 of p1. So we do the second encoder, and the second encoder will increase the depth till 64. The height and width will remain h by 2 and w by 2. And by the way, like the initial height and width are 128 and 128. So that's over here. So this is over here. This is the inc2. So let me delete a bit. So this is inc1. I will write e1. Then we do p1, the first pooling layer. Then the inc2. This is the inc2, e2. The inc2 means the second encoder. Then we do the second pooling layer, p2. So we do p2 equals self.pool2, and it will become h by 4 and w by 4, and as I said again, it's 128, and the depths will remain the same. Then we apply 128 filters of dimensions 3 by 3 with the same depths, which is 64, and this is self.inc3. Then we do the pool 3. Then we do the bottleneck, and the bottleneck is nothing but like the block over here. So this is the bottleneck. Okay, and now we're gonna start climbing above in the decoder. So that's how that's how the encoder part we do. So that's like the first part. So E1, P1, E2, P2, E3, P3, and then bottleneck, and that's what like is shown in the code over here. Sorry, S1. So S1, P1, S2, P2, S3, P3, and bottleneck. Now for the decoder part, we just do upward convolutions. However, as you can see, so let me erase a bit. As you can see, when you do the upward convolution, you have to concatenate. So you have to concatenate the incoming equivalent part. So here we have the S3 or E3, however you want to call it. So we have S3, we want to concatenate it with what's coming from the upward convolution part. So that's why this is the bottleneck. We're doing upward convolution. So up 3 of the bottleneck with S3, and that's the D3 for decoder 3. Then we do D2 is self dot up convolution 2 of so we're taking D3 and we're concatenating it with the parallel to it from the encoder part, which is S2. So if you look over here, here we have S2, we're concatenating it with D3, and we're doing up convolution. So that's why it's up between D3 and S2. And here I specify the dimension, which should be 64. And then we do up 1. And then at finally we do the output layer is self.outC of D1. Now we want to specify what's inc1, pool 1, inc2, pool 2, inc3, pool 3, and up 3, and I don't know what. First, let's define our encoder. So our encoder is nothing but so we import torch.nn and we do nn.conf2d. We specify the input dimension, the output dimension, like the dimensions of the filter, which are 3, and here we specify padding of 1, and that's it. Then we do batch normalization. Then we do a reload. Then we do conf2d again. However, this time around, the depths is no longer input depths. Now it's output depths. That's why we have output here and we have output here in the second one. Just a reminder. For example here, let me delete. For example here, the input dimension was 1. Here it became 64. So the first encoder had 1 and 64 in the input and the output. However, from here to here, we were 64, we remained 64. And that's why the second convolution has out C and out C over here. Then we do batch normalization, we do reload, and just for the overfitting sake, we do a dropout. Okay, guys? Regarding the up convolution block, so we do, in the up convolution block, we do the inverse of a convolution. So that's why it's conf transpose. We specify the input dimension, the output dimension. And as I said, the filter size can be whatever you want. Here I put a size of 2. And because we want to double the height and width of the image, we put a stride of 2. And so here we did our up block. So this is nothing but this arrow. So this arrow is the first is this line, and after we specified our up block, we now have to do a convolution. So if you look again, we now have to do a convolution over here. And because we have to do a convolution, we specify self.convolution is a convolution block. The input dimension is the output dimension times 2, because we have an output dimension from the arrow up, and the skip from the encoder also has an output C. That's why the input is out times 2, and the output should be output. So we're kind of reducing the depths by 2. Again, if you look over here, we had 1024, it becomes 512. Here also we had 512, it becomes 256. And yeah, that's it. So that's our up convolution block, and we get the image, and then we apply them in order. And finally, we specify our inc1, inc2, pool 1, pool 2, pool 3, and the bottleneck and the up convolution blocks. We just call these two classes, the up block and the conv block, and we give the dimensions. Okay, guys? And here we just put a class for the losses. So here we have it's just like a normal loss function, okay? And yeah, that's it. We specify in our model, we specify how many classes. Here we have 3 classes for the background, for the cat, and for the border, and that's it. Now, so let me run this. Now for our training, we specify our optimizer to be Adam. We also have to first we load the data, okay, and at every epoch we have to do our prediction and calculate the loss. So here I specify that we have 60 epochs, and for every epoch I just got the training time to see how much time it's taking, and yeah, that's it. And here I made a function that like visualizes the batches. So let's run it. Okay, so it's of course it's gonna take a lot of time because we have 60 epochs. Not too much, but like it'll take a good amount of time. So let me pause the video. So I pause the video so you don't have to wait with me. So at the end of the training, which would take approximately like 18 by 60, like I don't know, like less than 20 minutes, we'll have a training loss of around 0.13, and unfortunately the valuation loss is 0.51. It means we are kind of overfitted to our training data. So here I wrote a function to visualize the results. So we're visualizing for 20 different images. So here we have the ground truth. This is the input image. This is what the output should be, and this is the prediction. So it fails to capture the whiskers. Here also, like you can see, it doesn't like see the legs because it's kind of hard. Here also you can see the prediction and the original image. This looks actually quite nice, so it's kind of hard to see the whiskers. This is a bad prediction, honestly. This is also good. Like, okay, so you can have fun with it, guys. And also I wanted to visualize at every step, so I wrote this function. You can read it. So it basically visualizes at every step how what the model sees. So after the first encoder, after the second encoder, after the decoder. So let me just run it and turn it on for you guys to see. So and by the way, we're seeing it like a heat map because I specified that I wanted it to be like a heat map. So after the first encoder, this is like one of the images, what it looks like. The encoder block 2, and I place them on top of each other, and as you know, like we have many channels because we have a depth after the first encoder. So like here are some of the visualizations that you may see. Here are some of the images that are generated. This is after the second encoder. here is after the third encoder. So as you can see, we are losing fine details, as you can see. But apparently these help the network. So this is at the bottleneck before the decoder. These actually help the network detect where the cat is. So if you look at them, I mean, you may be able to. Oh, what's this over here? You may be able to like figure out what they are really. So we have 1024. I just visualized 11, but like when these actually help the network detect where the cat is. After the first decoder, here are the images. After the second decoder, here are the images. Third one, as you can see, as we go up, it's more and more finding out where the image is, and voila, that's it. And here I visualize the concatenation. So this is from the upward convolution, this is from the encoder, and we place them on top of each other, here as well, here as well, and yeah, this is at the very first layer, the concatenation, and this is the final output, the input image, the ground truth, the prediction, and how it did it. So I hope you enjoyed the video, guys. We talked about the architecture. We implemented it from scratch. I'll be providing the code in the link in the description. But if you're using it for your project, okay, you may use it. You can change the dataset if you want. So all you need to do is you go up to the dataset loading cell, and you change these two lines over here. However, you have to provide the same transformations or you'll get into an error. If you go into any problem, you can message me on LinkedIn. I'll put the link in the description. And what I encourage is, okay, you can take the code. However, I'll also be providing a lab, which is this code. However, the important details that will help you understand the Unet would be commented out. So let's say I'll be removing some of these parts over here, and I encourage you to try to implement the lab instead of just taking the code for you to learn. If you have any questions, leave it in the comments, and I'll see you again, guys, in another machine learning paper implemented. Bye.